The James Webb Space Telescope is a collaborative project between NASA, the European Space Agency, and the Canadian Space Agency. It's designed to be the premier observatory of the decade, aiming to revolutionize our understanding of the universe. Launched on December 25, 2021, aboard an Ariane 5 rocket from the Guyana Space Station in South America. By January 2022, it reached its destination, approximately 1.5 million kilometers away from Earth. Webb is equipped with advanced instruments that allow it to observe the universe in ways never before possible. Its primary mission objectives include the study of the formation of galaxies, stars, and planetary systems, as well as investigating the potential for life on exoplanets. As the successor to the Hubble Space Telescope, Webb has built upon and surpassed the discoveries made by its predecessor. With its larger mirror and more advanced technology, Webb has provided even sharper and deeper images of the cosmos. The primary mirror of the Hubble Space Telescope is a single mirror with a diameter of 2.4 meters, made of solid glass coated with aluminium. In contrast, Webb features a segmented mirror composed of 18 hexagonal segments, totaling a diameter of 6.5 meters, made of lightweight beryllium coated with a thin layer of gold. Hubble primarily observes in the visible and ultraviolet spectrum, while Webb is specifically designed for infrared observations. This was the first image from Webb. This galaxy cluster is in the southern constellation of Volans. At the heart of the image is a bright elliptical galaxy, surrounded by smaller galaxies. These galaxies, bound together by gravity within the cluster, act as a cosmic lens, bending light from distant galaxies behind them. The mass of these galaxies creates a magnifying effect, distorting and sometimes duplicating the images of individual galaxies. In 1995, the Hubble Space Telescope imaged the pillars of creation, where stars form within dense clouds of dust and gas. Imaged by Webb in near-infrared light, these columns measure 4 to 5 light-years across. This was one of the early images from Webb, and it has gone on to produce stunning images and increased our understanding of the universe. So, where is the James Webb Space Telescope? After traversing a distance of 1.5 million kilometers in roughly a month after launch, Webb reached its destination, the Sun-Earth Lagrange L2 point. Lagrange points are locations in space where the gravitational forces between two celestial bodies, such as the Sun and Earth, create regions of increased attraction and repulsion. These points serve as advantageous positions for spacecraft, allowing them to conserve fuel and maintain a stable position without continuous propulsion. They act as convenient parking spots in space, enabling spacecraft to remain stationary relative to the bodies involved, with minimal energy expenditure. Staying stationary relative to the Earth and Sun at one of these 5 points is relatively straightforward for a spacecraft. Specifically, L4 and L5 are stable, meaning objects positioned there will naturally orbit around L4 and L5 without any external assistance. However, the stability of L1, L2, and L3 points is different. They are metastable. Objects positioned around these points tend to slowly drift away into their own orbits around the Sun, unless they actively maintain their positions. This maintenance often involves using small periodic rocket thrust. Consequently, unlike L4 and L5, L1, L2, and L3 points do not accumulate objects over time. Our understanding of the Lagrange point resides within one of the most formidable challenges encountered by mathematicians and physicists for the past 4 centuries, the three-body problem. The three-body problem refers to the mathematical challenge of accurately predicting the motions of 3 celestial bodies, such as stars, planets, or moons, interacting solely through gravitational forces. While the interactions between 2 bodies can be precisely described using Newton's laws of motion and gravitation, the introduction of a third body significantly complicates the scenario. When a third body enters the equation, there is no straightforward solution that can accurately predict the interactions among 3 objects through their mutual gravitational forces. In the modern era, only computers possess the computational power to analyze the intricate calculations and yield meaningful results. In contrast, our predecessors grappled with impenetrable mathematical puzzles, unable to navigate the complexities of unsolvable equations. The concept of the first three Lagrange points emerged from the work of mathematician Leonard Euler in 1760. Euler's investigations into the interplay of gravitational forces between celestial bodies led to the proposal of these points, where the gravitational forces balance out between two orbiting bodies, such as a planet and the Sun. Subsequently, in the early 1770s, Joseph Louis Lagrange, a student of Euler, expanded upon this idea and identified two additional points, known as L4 and L5, validating Euler's earlier findings. L1, L2, and L3 are situated along the line connecting the Earth and Sun, while L4 and L5 form the apex of equilateral triangles with the Earth and Sun at their vertices. L4 precedes Earth's orbit, while L5 follows. The L1 point in the Earth-Sun system provides an unobstructed view of the Sun and has hosted solar observatories including Discover, Wind, Soho, and ACE. Conversely, the L2 point accommodated the WMAP spacecraft, currently houses Gaia, Euclid, and the James Webb Space Telescope. The L3 point, concealed behind the Sun at all times in the Earth-Sun system, is unlikely to find practical application. However, the notion of a hidden planet X residing at L3 has captivated science fiction writers, despite the instability of such an orbit. The L4 and L5 points have no current practical application. We could speculate that there should be an accumulation of asteroids and dust at these locations, but any objects would need to be placed there with little momentum in order to stay at L4 or L5. To date, two asteroids have been discovered at L4. These are known as Trojan asteroids. Jupiter, by contrast, with its far greater gravitational pull, has hundreds of thousands of Trojan asteroids located in its L4, L5 points. It's not known how this formed, but may have happened during the early history of the solar system. The investigation of the Jupiter Trojans is one of the purposes of NASA's Lucy mission, which launched in October 2021. Lucy's mission will involve conducting remote sensing observations on 8 Trojan asteroids during 5 flybys. A popular idea is that L4, L5 could be home to potential space stations and off-world colonies. For now, this remains science fiction. So let's take a deeper look at how the Lagrange points work. The work done by Lagrange solved what is known as the restricted three-body problem, as the mass of the third object is negligible in comparison to the other two. This considers the effect of the opposing forces of the two larger masses and the centripetal force acting in the opposite direction as the Earth orbits the Sun. We are all familiar with centripetal force, the force which we experience when we swing an object around ourselves, and we feel the pull of that object away from the center of the rotation. At the Lagrange points, gravity and centripetal forces cancel each other. L1 is at the point at which the gravity of the Sun and the Earth cancel each other. That is the point at which we would not feel any pull towards the Sun or towards the Earth. Any closer to the Sun, and we would feel the gravitational pull of the Sun. Any closer to the Earth, and we would feel the gravitational pull of the Earth. L2 is at the point where the combined gravity of the Sun and Earth cancels the opposing centripetal force. L3 is the point on the opposite side of the Sun from the Earth, where again the combined forces of the Earth and Sun intersect the orbit of the Earth and counteract the centripetal force. It's important to note that the first 3 Lagrange points are unstable. To illustrate this concept, consider a perfectly smooth and frictionless saddle. Now imagine attempting to balance a marble right at the very center of this saddle. While it's theoretically possible, in practical terms, it's exceedingly challenging to achieve. The ball will tend to fall down the slope either side of the saddle. L4 and L5 lie at the point on the Earth's orbit where the gravitational force of the Sun and Earth are in balance. Any closer to Earth and there would be a pull towards Earth. Any further away and there would be a pull away from Earth on the path of the orbit. While L4 and L5 points are positioned at the peak of a hill in the gravitational potential contour plot, they remain stable. This stability arises due to a second-order effect. As a body deviates from the exact Lagrange position, Coriolis acceleration comes into play. This acceleration, dependent on the velocity of the orbiting object and not represented accurately by a contour map, curves the trajectory into a path around the point instead of away from it. The stability attributed to the Coriolis force results in orbits that are generally not planar, but three-dimensional, existing on a warped surface intersecting the ecliptic plane. The familiar kidney-shaped orbits, often depicted around L4 and L5, are merely projections of these orbits onto a plane and do not fully capture the three-dimensional nature of the orbits. The stability of the L4 and L5 points hinges on a specific condition: when the primary body's mass exceeds at least 25 times the mass of the secondary body. These conditions are met in the Sun-Earth system, as well as the Earth-Moon system. Webb is situated in an elliptical orbit on the Earth side of L2, not quite at the L2 point. If it were at the unstable L2 point, then it could fall away from Earth. The design of Webb has thrusters on one side and the scientific instruments and mirrors on the other side. If Webb fell away from Earth, then it would have to be turned around to reach L2, exposing the scientific instruments to the Sun. Not great for the mission. Webb has a 5-layer heat shield providing protection against the Sun. This elliptical orbit is similar in size to the Moon's orbit around Earth and perpendicular to the orbit of the Earth. The orbit Webb follows takes approximately 6 months to complete, ensuring that the telescope remains beyond the shadows cast by both the Earth and the Moon. The decision to adopt this large orbit was based on the ease of reaching the orbit. Objects further from their orbital focus move at slower speeds and demand less energy to maneuver. The larger orbit ensures that Webb will remain unaffected by the shadows of either the Earth or the Moon throughout its mission. The Lagrange points provide many opportunities for the location of satellites and the furthering of our scientific knowledge. The images produced by Webb have already made a huge contribution to our understanding of the universe. In this image, Webb has captured wonderful detail of the Crab Nebula, revealing its various components in remarkable clarity. Among these features are the expanding cloud of hot gas, intricate filaments of dust, and the distinctive synchrotron emission, the emission generated by the nebula's pulsar, a rapidly rotating neutron star positioned at its center. Located 161,000 light-years away within the Large Magellanic Cloud galaxy, the Tarantula Nebula stands as the largest and brightest star-forming region within the local group, the collection of galaxies nearest to our own Milky Way. Within its expanse reside some of the most massive stars ever discovered. Webb will continue to provide spectacular images as the mission continues over the next 8 to 10 years.